Hello guys, welcome back to my channel Gamma. I apologize for the brief hiatus on this channel, but I am back after successfully completing my internship. Let's get started with today's video, and mind you, the topic for today is pretty interesting, so pay close attention. So the topic of principal interest in this video is tensors. I'm introducing them in this video. So take this equation. The current density is equal to sigma, which is the conductivity, times the electric field. Well, fine, this equation is valid. This is the vector form of Ohm's law. This is perfectly valid. The issue is this this sigma here. What is it? Is it a scalar? Is it a vector? Or is it something else? Because think about this. The way I've written sigma, you can say it's a scalar. Why? Because assuming you have some material, some conductor, and there's some current density through it for an applied electric field, you basically solve the equation and you get sigma, which is, if you think of it as a scalar, it's going to remain same in all directions. So if you think that it's a scalar, it's going to remain same in all directions. If it's a function, it's going to be the same function in all directions. Now the issue is this only holds for materials where materials that are constant in all directions. So I'll say sigma is a scalar for materials that have constant properties. Yes, let me put it that way. Electrical properties in this case, in all directions. And these materials are called isotropic materials or media or whatever. But this may not be the case always. If you take some crystals, for example, they're not, sigma is not constant. Sigma in this case is a tensor for materials that have inconstant properties in different directions. So these are called anisotropic media or materials. Okay, so in that case it's a tensor, and when I write this out, when I write the correct version of Ohm's law, the current density J, which is a vector, is equal to the conductivity tensor applied to the electric field vector. And if I write this out in terms of like column vectors J1, J2, J3, I have this equal to sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3, applied to E1, E2, E3. And in this case it makes perfect sense to represent the conductivity tensor as this matrix, because it satisfies the equation. I mean, this is a matrix multiplication equation, which clearly makes sense. We can solve for E1, E2, E3 by inverting this matrix, this conductivity matrix. But this is not the general idea of a tensor. The general idea of a tensor is actually hard to write down without actually getting a little more mathematical and dry. This is a rank 2 tensor. That's why we can represent it by a matrix. Remember, a matrix is just a construction. It's an array of numbers. Until you think of a matrix as an element of the generalized linear group GL3, until then it's just a representation of either a rank 2 tensor like this case, or a linear transformation, which I will discuss shortly. So what is the idea of a tensor? So the idea of a tensor, for that, again, as I said, it's hard to like show visually what it is, but I'll try my best. Assuming you have some, I don't know, some 3D surface, a surface in 3 dimensions, that's a better way of saying that. I'm trying my best to draw here, please bear with me. Assume you have something like this. Say this is your, say, z direction. This is your x direction, and your y direction is sort of behind this way. All of these are mutually orthogonal. Well, consider this face which has a normal vector in the positive x direction. Call this face 1, for example, this entire face 1 of this cuboid. I wanted to draw a cube, but it turned out to be a cuboid, so this cuboid. Assuming you have some stress acting on this figure, this is a solid, so assume you have some stress acting on it. I'm sure the mechanical engineers out there are getting excited. Since this is face 1, a stress in the x direction on face 1, I can represent that as tau 1 1. Now a stress in the y direction but on face 1, I can represent as tau 1 2. And a stress in the z direction but on face 1, I can represent as tau 1 3. And I can do that with the face 3, the face which has its normal vector in the positive z direction, which is this top face. I can have some component of a stress acting in this of face 3, acting in the z direction, which will be tau 3 3, on face 3 acting in the y direction, which will be tau 3 2, some stress component acting in the x direction on face 3, which will be tau 3 1. And we can do this with face y, which will be behind. It's hard to draw, so I won't draw it here, but so you get the idea. Each basis component is made up of 2 basis vectors. This is for a rank 2 tensor, mind you. This is for a rank 2 tensor because rank 2 tensors are easy to draw, easy to represent. It's like drawing a 3-dimensional like representation or 2-dimensional figure. It's hard to draw higher dimensional figures. It's like that. This is a rank 2 tensors because each component is made up of 2 basis vectors. So if you look at each component of this stress tensor, which is represented by tau with these 2 lines on it. 2 lines means a tensor. Each of the components has 2 indices. It has one for the face and then one for the direction on the face. So it has 2 indices here. So if you say take an example of a vector, we had just one index, right? So one index, one basis vector. Each component had one index. Here each component has 2 indices. So it's kind of like sigma 1 1, and since it has two indices, it should also have two basis vectors, e1 e1. When I don't write anything in between them, we have a tensor product like this. I'm going to come to this, and we have all the permutations of 1 2 and 3, you know. But mind you, sigma 1 1 2 is not equal to sigma 2 1. They're entirely two different things. You can see it on this figure. The y direction of stress, the y component of stress on face 1 is not equal to the x component of stress on face y, unless, you know, there is some implicit symmetrical relationship, in which case the matrix will be symmetric. So there's no surprise there. Let me point out, if I use Einstein's subscript summation convention, this will look like sigma ij. I'm doing this for the conductivity tensor again. EIEJ, again, when I don't write anything in between, no dot product, no cross product, it's implied that I have a tensor product going on there. And this guy is not EI, it's not EJ, it's something entirely new. This is a new basis vector. This is the EI tensor EJ, sort of, not base, even a basis vector, basis tensor. EI, EJ were basis vectors, but a basis tensor of rank 2 is a tensor product of two basis vectors. So you can generalize this idea of saying that a tensor of rank, a basis tensor of rank, I don't know, let's rank k is a tensor product of k basis vectors. So just to generalize this idea, and before generalizing, let me just complete this notion of j is equal to, well, sigma, this is the tensor dotted with e. Use subscript summation convention here. Sigma ij, ei tensor ej dotted with el, el hat. If you just simplify things, and how the dot product works for tensors is that the basis vector that are basically facing each other in the dot product will get converted into a Kronecker delta for those two indices. So in this case, we will have a Kronecker delta JL, not a Kronecker delta IL, because J, E sub J and E sub L are sort of facing each other in this dot product. EL will come outside because it's a scalar. We'll have E sub I as it is multiplied with the dot of E sub J hat and E sub L hats, which will result in a Kronecker delta JL. Which, if you simplify things a little more, will be sigma sub ij, E sub J, E sub I hat. Okay, and it's easy to find JK. You just do another dot product and you simplify things. So this will be JK is equal to sigma KJ E sub J, I believe. So you notice this matrix multiplication going on, which clearly says that, you know, the matrix representation for a rank 2 tensor is appropriate because it's clearly satisfying properties here that we would expect of matrices in terms of matrix multiplication. If you remember, this was the expression for a matrix multiplication using subscript summation convention. Please watch the first video if you don't know what's going on here. Now let me generalize this idea. So tensor T, if I can write it as T sub I jk dot dot dot, we don't know how many basis vectors are there in one component. E sub I, E sub J, E sub K dot dot, all of these are tensored again. So the number of these guys So suppose this ends at n. So all of these guys, so let's see, n minus I plus 1 of these guys is the rank of tensor T. So how many basis vectors you have in a basis tensor, or how many of these subscripts you have in the subscript summation expansion of the tensor, is what determines the rank. And all these guys, I, j, k till n, they all belong to, say, 1 to x, and this x is the dimension. Since we are working on 3 dimensions, our x will be equal to 3, and it kind of makes sense, because if you remember the subscript summation for vectors, I only expanded the subscript till 3, because we were working in 3 dimensions. We were working in R3, so we didn't need to worry about higher dimensions, but this is a general notion. So the highest value that any subscript can take is the dimension, and the number of these subscripts is the rank of the tensor. We will mostly be dealing with rank 2 tensors because we can write them as matrices. Rank 3 tensors, if you suspect, will be sort of cubic matrices. So matrices that don't just have this front side but also, sides behind them. It's hard to represent this way, but I hope you see the idea for all of each row, each column. We have a sort of a cubic matrix, a 3D matrix. Rank 1 tensors, so these are rank 3 tensors. Rank 2 tensors are what I represented by matrices on top. So just refer to whatever I had on top. Now rank 1 tensors, which means each basis tensor has 1 vector, which means it is just a standard vector. So it's a regular vector. Rank 0 tensors, which means you don't have any vectors any basis vectors in one tensor components, which means you just have a scalar. So this is how you generalize quantities. Rank 0 tensors are scalars, rank 1 tensors are vectors. Rank 2 tensors are basically can be represented by matrices. Rank 3 tensors can be represented by cubic matrices. Rank 4 tensors will be like matrices where it's like the counterpart of like a 4-dimensional cube, like a tesseract or something. Okay, and finally, if I have, say, 2 vectors A and B, and there's nothing, I don't specify anything between them, there's no dot product, there's no cross product, and there's clearly no addition because I didn't mention that, then it's implied that there is a tensor product there. It would be mathematically more healthy to write a tensor product like this, like a cross with a circle on it, but I'm not doing it because it's a little time consuming. And if you expand it using subscript summation, this is what you get. And again, when I don't write anything, this implies that EI basis vector is tensored with EJ hat basis vector. So there you see this entire idea. So if you tensor up 2 vectors, you get a rank 2 tensor. If you take a rank 2 tensor, tensor it up with a vector, you get a rank 3 tensor. So that's how it goes. And again, as you might have suspected, we can only add tensors of the same rank, preferably the same dimension, but I mean it doesn't really matter in this case. I mean you can have something in 2 dimensions added with something in 3 dimensions, it won't change anything. This kind of makes sense because you can think of like adding, say, a scalar s with a vector v. It doesn't make sense, right? It doesn't clearly make sense. Unless you specify some direction for s. So, and you can add 2 vectors, you can add 2 tensors of the same rank. So it clearly, there's a clear analogy here, there's a clear sanity check here. Okay, let's now think about transformations, because we can also represent linear transformation as matrices. Please watch my playlist on linear algebra to get more closure on that. Vector v can be represented as v sub I e sub I hat. You can also represent this in another basis, the prime basis, which will be vi prime, v sub I prime, e sub I hat prime. And since it's a vector is like sort of like a standard idea, both these representations should be the same. They should represent the same vector. Of course, the components might not agree and the basis vectors might not agree, but when you apply them together, when you basically have them together, you get the a vector, the same vector. We are talking of linear transformations in this part of the video. So how to convert from the unprimed system to the prime system? Well, the vector v prime can be represented by a matrix small a applied to the unprimed vector in the unprimed system. And if the transformation is a rotation, then we can find a rotation matrix by keeping track of where the basis vectors land up. Please, if you don't understand what is going on here, please watch that linear algebra video on linear transformations. So this is the transformation matrix small a, in case your transformation is rotation, and we want our transformation to be structure preserving. So in a way, we want it to be isomorphic because we want this matrix to be invertible. We want to be able to freely convert from the unprimed system to prime system and the prime system to the unprimed system by taking the inverse of this matrix. We don't want like a projection matrix from like 3 dimensions to a 2-dimensional plane, because then you can't invert that clearly. Okay, so think of this as like, say you have your vector v, you rotate it by some angle, some theta naught, end up at v prime. So that's what this matrix is. It's mapping vectors in unprimed system, or say vectors like input vectors v to their rotated counterparts v prime. And we clearly have a sort of a inverse for this, just reverse the rotation or change the angle to a negative. So we have vi prime is equal to, I want to represent this by a matrix because we can represent linear transformation by matrices, a sub ij v sub j. This is subscript summation for matrix multiplication. V vector is v sub k e sub k hat is equal to v sub I prime e sub I prime hat. Again, just using the same idea of the vector being invariant. V sub k e sub k hat, a sub ij vj. I can use this relation now, e sub I prime hat. Now, assuming your vector v was just standard basis vector e sub m hat, this would mean that v sub k e sub k would just be e sub m, and we would have a sub I m and a component of e sub m, which is 1, e sub I prime. Pause the video if you don't understand what just happened. It should be pretty clear. So what this implies is that dot both sides, you get this relation a sub nm is equal to e sub n prime hat dotted with e sub m hat, which means the dot product of the basis vector in the prime system with the unprime system is a matrix, is this transformation matrix that basically converts the vector component from the unprimed to the primed system. So these guys are pretty closely related. This relation just proves it. So the first subscript is for the prime system, second subscript is for the unprimed system. That's a good way to remember this relationship. Okay, so now assuming you have the position vector, because we dealt with this in terms of curvilinear transformations, you can write this as this in a standard basis. You can also write this as d x sub j prime e sub j prime, and you can use the same logic as before. D sub xi is equal to a sub ij d sub xj prime. Now what is d sub xi? You can use the chain rule here. We have partial xi prime x1 x2 x3 with respect to, say, x1 dx1 plus partial xi prime x1 x2 x3 respect to x2 dx2 plus partial xi prime x1 x2 x3 with respect to x3 dx3, and dx sub I prime, we can also use sort of the chain rule here. Partial x sub I prime x1 x2 x3 with respect to xj dxj. I'm sorry, there was supposed to be a prime there. So I've just used the chain rule on top and then sort of used subscript summation for x1 x2 x3 using x sub j, which means you can see the clear relationship here. This means that a sub ij is actually this partial derivative calculation x1 x2 x3 respect to xi. And if you remember what this is a Jacobian, or you can think of this as probably like the vector gradient. These two guys are just like transposes of each other. So I don't care what the indices are, if they're the transposes or not. I'm just saying it out aloud. So there's like an intimate relationship between these differentials in the regular Cartesian system and in this primed system. Rather, the unprimed and prime I didn't specify it as a Cartesian. So assuming you have e sub j, we can write this as a sub ij, e sub I prime, and we have e sub j dot e sub k. This is equal to a sub ij, e sub I prime dot e sub k, e sub j hat dot e sub k hat is basically equal to a sub ij, and this guy is just a sub ik using the definition or the formula we derived for this transformation matrix. This is just a times a transpose, but we know what this guy is. This is just the Kronecker delta jk, and the matrix version of the Kronecker delta is the identity matrix. So yeah, there we have it, the identity matrix, which means that for this transformation matrix A, it's symmetric because the transpose is equal to the inverse. This again is because we are just defining this for orthogonal systems when we have a clear definition of the dot product this way to be the canonical delta jk. We have e sub I prime dot e sub j is equal to partial x sub I prime x1 x2 x3 partial x sub j e sub I dot q sub j hat is equal to partial x sub I q1 q2 q3 with respect to q1 q sub j, my bad. I'm just changed the prime to the Cartesian system, the unprime to the regular curvilinear system. So what we can do is we can just multiply by a Cartesian basis vector up front, partial xi q1 q2 q3 with respect to q sub j e sub I hat, and now this guy just becomes partial derivative of the position vector with respect to q sub j. There should be a partial here, I'm sorry, q1 q2 and q3. If you remember what this is just the scaling factor times the Cartesian basis vector is equal to, now this guy is just a sub ij e sub I hat, because the Cartesian was the prime, so the prime index comes first, which means we have a clear relationship between the curvilinear, general curvilinear basis vectors. So a sub ij divided by the scaling factor times e sub I hat. If you remember, I had defined matrices in the last video, so please watch the last video, because you'll clearly see that this matrix along with the scaling factor clearly makes sense, because we look at them in terms of linear transformations, but back then the matrix was just a convenience notation to represent all three basis vectors, but now it just clearly makes sense from the perspective of linear transformations. So it's all beautifully connected. That's how math is great. Okay, so if we have, say, our vector v sub I e sub I hat is equal to v sub j prime e sub j prime hat, and we have our tensor represented at, say, rank 2 tensor t sub ij e sub I hat tensor e sub j hat, and we have the tensor, the same tensor expressed in a different, like a prime system. So t prime sub rs e sub r prime e sub s prime, both tensored again. Do the dot product with, say, e sub l hat, which is a basis vector of the unprimed system. Well, t sub ij is a scalar, so it comes out e sub l hat dot e sub I hat. Again, the order is important. We have to take I, not j. Will give us, say, t sub ij canonical delta il. Canonical delta il. E sub j hat is equal to well, there was no prime. I'm sorry about that. T prime sub rs, well, e sub l hat dotted with e sub r prime, again take the first component in the tensor product, will give you the matrix a sub rl, because that's how we define them, right? The primed system dotted with the unprimed will give you a sub primed index times unprimed index. Okay, now do another dot product. Well, first contract over the index. I would highly advise that, which means change all the i's to l's. So tlj e sub j, and we can dot this with, say, e sub p and dot product on the right hand side, not on the left hand side, because anyways it doesn't matter now. There's just one basis vector here. So here we get T sub Lj, Kronecker delta Jp, T prime Rs, A sub Rl, A sub Sp, if I'm not wrong. And if you want to represent this in a better way, just contract over the index again, A sub Rl, A sub Sp. And if you want to write this back in a matrix form, this is just going to be matrix T is equal to, well, A transpose, we want the second index to match, matrix of T prime. So this matrix, each coefficient of this matrix, each element of this matrix is just the component in the prime system. Each element of this matrix is the component in the unprimed system. A is the constant transformation matrix between the two systems. This is what this looks like. And if you remember, this is just like the formula for changing or writing a matrix in a different basis. Again, this shouldn't come as a surprise. Although these are tensors, we are representing them as matrices, and we are doing so because we have reason to do so. The product worked out like a matrix product. The transformation laws work out like matrix laws. So this is more than enough justification that we can represent rank 2 tensors as matrices. This formula is the formula for representing a matrix in a different basis when the transformation matrix, which is not the same as this guy, I mean T prime and A are different. When the transformation matrix, which means the A, are orthogonal, otherwise we would have to take inverse, and this would be A T prime, say A inverse, something like this, if they weren't orthogonal, the matrices. But again, this is again the basis change formula for a linear transformation that's represented by a matrix. Okay, so the advantage of tensors, again, apart from just representing all those properties in anisotropic media, is writing stuff in a mixed basis. So what I mean is, take vector form of Ohm's law. Let me write it down. I shouldn't make a mistake. Well, J sub I, E sub I hat is equal to, if you represent this tensor in the prime system, it will be sigma prime sub jk, E sub j prime, E sub k prime, dotted with, say, E sub L hat. This just becomes sigma prime sub jk, EJ prime, because we're doing a dot product over this. So E sub k prime dotted with E sub L will give you transformation matrix A sub KL. So this is just for J sub I, E sub I. If you do another dot product to get JI, E sub L, you get transformation matrix JI A sub KL. So it doesn't matter what basis you write your tensor in. We can always, if as long as we have this transformation matrix between those two bases, we can establish a relationship between them. So the idea of tensors was that it was sort of basis invariant. I mean, you can say vectors are basis invariant also, but tensors are just a generalization of them, and we need generalizations, especially when we talk of things like general relativity. And that's exactly the language that general relativity is written in, because one frame of reference, one coordinate system is not enough. Space-time is changing, so you treat it as a manifold. You look at the locality of things, and that's what you call differential geometry. I demonstrated like a basic tenet of this in probably like 2 videos before, so watch that if you haven't. But the idea of this invariance is really handy. This, irrespective of what basis you write anything in, it's really important when we try to find general relativity or write equations, Einstein's equations in general relativity. Now, since we can write in any basis, why not choose a convenient basis, right? I mean, let's make life easier. We don't like these big ass calculations. We want our inverses to be as, computationally cheap as possible. We don't want to spend too much computer space, time, and energy on that. So choosing a convenient basis, that's where diagonalization comes in, or converting each matrix representation of a tensor into a diagonal matrix. Again, this shouldn't come as a surprise, because we can diagonalize matrices themselves if you treat them as like independent entities, or elements of, say, GL3. So if you can diagonalize a matrix, this means that the diagonalization should have some physical significance when it comes to representing tensors as rank 2 tensors as matrices. And it clearly does. See how these things are connected. Rank 2 tensors are connected to matrices, which are connected to linear transformations and entire linear algebra thing, concepts, ideas are all connected. So there's like a direct correspondence. There's a isomorphism on these guys, and these dictionaries from like moving from one branch of math to the other. Because what we're doing now is functional analysis. We're working with tensors and vectors. Moving from functional analysis to linear algebra is not such a remarkable dictionary if you think of greater mathematics, but it's certainly powerful and is important. So that's why math is beautiful. That is basically the conclusion of this video, because you can combine, you can sort of correlate ideas beautifully from one branch of math to the other. Everything's connected. It's just nice. Before ending this video, I would like to make a note that I'm not differentiating between contravariant and covariant components, or I'm not even writing differentiating between subscripts and superscripts, because the thing is, we're dealing with orthonormal systems, not even orthogonal systems. So the dot product of even general curvilinear basis vectors is chronicle delta ij, so we don't need to worry about them. If they're not, for non-orthonormal systems or non-orthogonal systems, we need to worry about covariant and contravariant components, stuff that will basically give us chronicle delta and stuff that won't. So further breaking down components to themselves. So it's a complicated thing, and I'm not covering it in this series, because this is at the level of, say, introductory mathematical physics. So there you have it. I hope you enjoyed this video. I hope you learned a lot. Please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Di Gamma in the math community. In the meantime, stay home, stay safe, keep doing math, and officially, peace out.